Hi students, continuing our discussion of EMI, electromagnetic induction. In this part we are going to see about the motional EMF. Now in the last video we have seen, as per the Faraday law, the induced EMF is equal to negative of the time rate of change of the magnetic flux, E equal to minus d phi by dt. The EMF is getting induced because of the varying nature of the magnetic flux. Now flux can be varied either by varying magnetic field or area or the angle between magnetic field and area, or by any combination of these, or by varying any combination of these three. Now induced EMF equal to minus d phi by dt. Induced EMF is coming because of the varying flux. Flux is equal to BA cos theta. Flux can be changed if you change B or A or theta or any combination of this, means either by changing B, A and A, or by changing B and theta, etc. Now depending upon that how we have changed the flux, EMF has been classified in two categories. Induced EMF has been classified in two categories. One is the motional EMF and other is the induced field EMF. The EMF which is arising due to motion of some part of the circuit. Some part of the circuit is moving in the magnetic field. Because of that reason, what is the EMF is arising? That we call the motional EMF. And the EMF which is arising due to the time varying nature of magnetic field, that part we call it as the induced field EMF. In this particular video, our main concern is going to be to discuss the motional EMF. The EMF which is arising due to the time varying, due to the motion of some part of the circuit, in which some cutting of field lines is taking place, that we are going to see in this particular part. Like for example, say for example, magnetic field lines are towards you people, like from me it is coming towards you. Some ropes like this you can say. And if I move this conductor like this, then I have to cut the field lines. Then it is cutting of field lines. Then EMF induced in this will be motional EMF. Another case you can take, if say for example, field is towards you only and I have to move it in this way, then I have to cut the field lines. Then EMF induced in this way is termed as the motional EMF. Now motional EMF as such is of two parts. In two parts we study, one by one we will see. Now motional EMF is due to the movement of some part of the conductor. This can take place in two ways. One, phi equal to BA cos theta. If we change the area, then also some movement is taking place. If we change the theta, then also movement of something is taking place in the circuit. The flux, the EMF which is arising due to the change in value of theta is shown on the left side. That also comes in the motional EMF. The EMF which is arising due to the change in area, that is shown on the right side. This is also motional EMF only. Now, due to change in orientation, due to change in theta you see, let us consider one coil. One coil is there. Say this coil is of area A, and its area vector is into the board and magnetic field is also into the board. So the angle between area vector and magnetic field is 0. At t equal to 0, the angle between the magnetic field and the area vector is 0. Now we start rotating this coil, and at any moment, let us say the angle between the magnetic field and the area vector becomes theta. Now as the theta is changing, the flux linked with the circuit is going to change. Let us assume it is moving with constant angular velocity, rotating with constant angular velocity omega, then this theta will be equal to omega t. Then at this moment, at this time, the flux can be written as BA cos omega t, because the angle between the area vector and the magnetic field becomes omega t. If this coil is made up of n turns, then we can write NBA cos omega t. EMF induced is equal to minus d phi by dt, that will come out to be minus NBA omega sin omega t with minus sign. So it will become NBA omega sin omega t. So this is due to the change in orientation. This is also due to the motion. This is also a part of motional EMF. But even though when we say motional EMF, we doesn't mean that, we mean mainly this part. And we are going to concentrate now mainly on this part. Now this also you see. If say for example, I have considered one magnetic field which is into the board and one conducting rod is there, say AB, it is moving in this direction, means perpendicular to the field lines. Field lines are towards the board and they are moving this way, conductor is moving this way. Now if I say that what is the flux linked with this movement of the rod in time t, then I can say in time t it sweep out an area of this much. This is the area it will sweep out in time t, Vt. Then what is the angle? Say area vector inside, magnetic field inside. So what is the angle between the area vector and the magnetic field? It is 0. Then we can say flux is equal to B A. A is equal to, if this length of the rod is L, if this is L, then A is equal to L into Vt, and cos 0 is 1. Then EMF induced will be minus d phi by dt, which will come BVL. Now this is only one situation where BVL is coming. We are going to discuss this in detail, very much detail in the coming part. Here only I am trying to say motional EMF is either due to change in theta or due to change in area. Here area is changing because at time t1 this will be the area, at time t2 this area will be added, this time t3 this will be the area. So area changing, because of that EMF is induced here. This is also motional EMF, and in default case motional EMF means this only. Now continue this particular part in detail. Now let's see how this EMF is getting induced. It is very conceptual point what we are going to see now. You have to pay attention and understand it clearly. We are considering any conducting rod. This rod is conducting rod. Remember, we cannot have any non-conducting material here. It is necessary that this material is conducting in nature. We are considering a conducting rod AB. which is placed in a magnetic field. Magnetic field is into the core and rod is like this. And we are moving this rod in this direction. We are moving the rod in this direction. Now, because of the motion of the rod, the free electrons present in the rod are also having the same velocity v. So, if a charge particle means these electrons are moving in a magnetic field, then moving charge particle in magnetic field experiences a force. From this concept, we can find what is the force experienced by them. So, velocity of the charge, magnetic field direction, and force will be downside because negative charge. Force will be downside. So, these electrons will experience the force in the downward direction equal to Fm. And the value of Fm will be minus E V cross B. Right? Even though for this particular shown situation, angle between the velocity vector and magnetic field is 90. So we can write it as here VB sine theta only. But I want to write in vector form, then we are going to have the expression which is in general can be used anywhere. So they experiences the magnetic force. Because of this magnetic force, the electrons will start drifting down. Electrons will start moving down. As a result, what will happen? Some accumulation of electrons will take place here. Accumulation of electrons will take place at B. Electrons accumulates here. And some electrons will drift away from here. So as a result, this part acquires the positive charge and this part acquires the negative charge. Because of this accumulation of positive and negative charge, an electric field will be developed from A to B. Electric field will be developed from A to B. This electric force will exert the electric field will exert the force on the electrons in upward direction because electrons are negatively charged. That force will be Fe. That force will be Fe. Fm downward, Fe upward. And a dynamic equilibrium condition will be achieved when the net force experienced by the electron will become 0. So the electric force becomes minus EE and the total force becomes 0. And this total force we can say minus EV cross B is equal to EE. So we have the electric field developed here minus V cross B. Now because of this electric field, a potential difference developed between end A and B. Between these two ends, an EMF will develop. That potential difference is equal to minus E dot dl. This comes out to be minus E is V cross B dot dl. So the total induced EMF will become integral of V cross B dot dl. What we have written in the last VBL due to the change in area, the last part. Now VB, so force is in this direction. So if those two are perpendicular, angle between these two is 90. Angle between these two is 90 and it becomes VB. And what is the direction of this vector? V cross B, this side, and DL is also this side. So angle between V cross B and DL is 0. So it becomes VBL in the previous case, right? So the induced EMF, the motional EMF is given by V cross B dot dl. V cross B dot dl. It is valid for uniform, non-uniform magnetic field as well as for varying length means arbitrary shaped conductor. There is no assumption we have taken. If you write this only for a small segment, then also it is going to be valid, right? Now let's discuss this particular part in depth. If the conductor is placed in uniform magnetic field, then this expression will become V cross B. Then this becomes constant and this reduces to V cross B dot integral of dl, and this can be written as V cross B dot L. Done. Try to understand. Let us consider any arbitrary shaped conductor is there. This. It is moving with some velocity vector v in a magnetic field B. You have taken a small length dl vector, and for this you have used this formula. Then V cross B dot dl, V cross B dot dl for this part, for this part, for this part, you will find. V and B both are same for all. So this particular part has come out from the integral, and integral of this is nothing but the vector joining the end points of the conductor. Means for this particular conductor, you can replace it by this conductor, this one of length L vector. This is your L vector, right? It again also means if I am having 3 conductors, say this, why 3? Say 4. 1, 2, 3, 4. If you see, all are having the different shapes, different sizes. But if these all conductors are moving with the same velocity v in the same uniform magnetic field, then EMF induced across these 2 points will be same, equal to V cross B dot L. L is the vector joining the end points of the conductor, right? Now we will see the polarity of the induced EMF. Means when this particular thing has been developed, induced EMF has been developed, this point will be at higher potential or this point will be at higher potential. This is what we are going to see. Now let's see how to find the polarity of the induced EMF. I'll suggest it is a very nice thing to remember, because throughout the magnetism you might have observed that direction plays a very important role. Here, how to find the polarity of the induced EMF. We are considering one conducting rod which is moving in the magnetic field is into the board, and in this direction it is moving. Now, which point will be at higher potential? Point A or point B? Which will be at higher potential? This is what we are going to see. Now, there are 2 rules to find the polarity. One is the Fleming's right hand rule, and the second is the right hand palm rule number 3. Palm rule number 1 and 2 we use to determine the direction of magnetic field and to determine the direction of magnetic force. Now, according to Fleming's right hand rule, you have to stretch the thumb, forefinger and middle finger of your right hand in 3 mutual perpendicular directions, like this, right? You have to stretch your thumb, forefinger, middle finger along 3 mutual perpendicular directions. Now, this you point towards the magnetic field. Magnetic field is into the board this way. Thumb you point towards the velocity. Middle finger will point towards the higher potential. Once again, these three, this towards magnetic field, this towards the velocity, and this towards the higher potential. So this way, A is at higher potential than B. So here we can say the polarity of point A is at higher potential. Now, if we have to use the right hand palm rule number 3, according to right hand palm rule, stretch your right hand palm in such a way that thumb and fingers are perpendicular. Now, point the fingers towards the magnetic field, thumb towards the velocity. Outward normal to the palm will give you the higher polarity and high polarity end. So, same thing you will get from here. Once again, right hand palm rule number 3, fingers towards the magnetic field, thumb towards the velocity, outward normal to the palm gives you the higher polarity. So this will come. So if here I say the angle between the V and L and B, all three are mutually perpendicular, EMF is equal to V cross B, that is VB dot DL, that is L, then it will be BVL like this. Now this we can, if this rod is having some resistance R, then we can say this rod can be replaced by a battery whose EMF is BVL and resistance is R. And then we can solve the normal circuit in the same way. Right? This is about the polarity of the induced EMF. Now I'll summarize it, this part, motional EMF. Motional EMF is due to two parts, due to the change in the theta orientation or due to the change in area. Generally the change in area is, we are saying motional EMF corresponding to the change in area. Due to the change in orientation, if any coil is rotating at the angular velocity omega in a magnetic field, then EMF induced in that coil will be NBA omega sine omega t, which is also a very normal general procedure for the alternators generators. And if I see towards this side, right side, which is arising the motional EMF, which is arising due to the change in area, then here the induced EMF is arising because of the motion of the electrons in the conducting part, and that is causing the EMF to be developed across any small part of the conductor given by V cross B dot DL. Polarity of this induced EMF is given by either the Fleming's right hand rule or the right hand palm rule number 3, and if this any extended object is there, any extended object is moving in a magnetic field, then we have to integrate the expression V cross B dot DL. This is all about it. Now let's have some questions. Let's take the first question. In this question, we are having one conducting rod AB which is moving with velocity V in a magnetic field B, uniform magnetic field. B is into the plane of the board and velocity is making an angle theta with the length of the rod. We have to find the EMF induced across AB. What is the EMF induced across A and B? And we also have to find the polarity, that which particular end is at higher potential, A or B. Now EMF induced is equal to, we know, V cross B dot DL. So let's find this. V is in this direction, B is into the board, so V cross B is in this way. So the direction of V cross B, we got this one, direction of V cross B. V cross B vector is in this direction. Angle between V and B is 90 degree, so VB, this comes. And with this length, small length DL, it is making an angle of pi by 2 minus theta. Angle between this DL length and this V cross B, it is pi by 2 minus theta. So it will become DL, A cross B is AB cos theta, So V cross B dot dl cos pi by 2 minus theta. It will become VB sin theta integral dl. And this dl has to integrate from here to here. So we'll get 0 to L and we will have VBL sin theta. So the EMF developed across A and B will be VBL sin theta. And what about the polarity? Velocity this way, magnetic field this way. So electrons can move. You can also do it this way. You can resolve this velocity in these two directions. It is V sin theta, it is V cos theta. Due to this component, no EMF has been developed. Due to this component, only EMF has been developed. So velocity, this magnetic field, upward. So point A will be at higher potential with A at higher potential. Understood? Simple question. Let's take the next question. We have one conducting loop A, B, C, D. This is placed in a magnetic field, uniform magnetic field B0. In this entire region, magnetic field B0 is present. And this loop is moving with constant speed V0 in this direction. This is moving with constant speed V0 in this direction. And the length of ADC is L0 and length of ABC is L1. So arc length ABC is equal to L1 and ADC length is L0. And we have to find the EMF induced across ADC and across ABC. And also the EMF induced across the entire loop. This is what we have to find. Now, EMF induced is V cross B. Now, if you see, this is placed in uniform magnetic field. In uniform magnetic field, if any conductor is moving any arbitrary shape, the EMF induced across its ends will be same as V cross B dot dl dot L, V cross B dot L, where L is the length of the vector joining the endpoints. Means for this part and for this part, we are going to have the same induced EMF. Now what is V cross B dot dl? V naught, B naught into L naught. V naught cross B naught in this direction, vector product this and this length, both are in the same direction, dot product is then V naught, B naught, L naught. Since this and this both are to be same, this comes out same as V naught, B naught, L naught. If I want to replace this by an equivalent part, then it will be like this, A, B, C, and ADC will be like this, A, D, C will be like this, and EMF of both will be same, equal to V naught, B naught, L naught. Now we are to also find what is the EMF induced across the loop. Then it is very simple. You see, EMF induced across the loop minus E plus E. So it will become minus V naught, B naught, L naught plus V naught, B naught, L naught, and answer comes out to be 0. Now there is one very easy way also to tell this. Now as it is moving from here, some field lines will enter and equal number of field lines will pass from here. The flux linked with this loop is constant. So EMF induced in the loop will be 0. And since EMF induced in the loop is 0, the EMF induced across ADC and across ABC must be equal and opposite. so that the vector sum means KVL, if you apply and find, this will become 0. Let's take the next question. Let's see this one. In this question it is mentioned, it is in the horizontal plane, two conducting rails are there. The ends of parallel, the ends of which are connected to a resistor R. And one movable conductor is there of length L, and this length is L. And this conductor is moving in this direction with constant velocity V0. With constant velocity V0, it is moving in this direction. We have to find the current in the circuit, and we also have to find the force to be applied on conductor. This conductor is having the mass M, on conductor to make it to move. With constant velocity. To move it to constant velocity, what? It is like this, two U-shape, one resistor, this conductor, magnetic field is into, and this arrangement has been shown to you in this way. Now it is going to move. When it is moving with constant magnetic field, constant velocity, then an EMF will induce across this. EMF will induce across this. What is this EMF? V, B in this direction, then EMF induced VBL. So this is equivalent to this resistor and a battery of EMF V0 BL. Because of this, a current is flowing I. By applying the KVL minus E plus IR equal to 0, you got the current as V0 BL divided by R. Current comes. It means in this particular rod, current I is flowing. Current I is flowing like this, upward. Because of this current, a current carrying conductor in magnetic field experiences the force I B. So force is acting in this direction, magnetic force equal to IBL. So this rod experiences a magnetic force equal to IBL FM. I is V0 BL upon R BL. So you got V0 B square L square upon R. This is the force acting. But this rod is moving with constant velocity. If this rod is moving with constant velocity, some other external agent has to apply an equal and opposite force so that the net force is 0. So the force applied so that it moves with constant velocity must be equal to this value, and direction will be opposite to Fm. So its velocity, its magnitude will be B square L square V0 by R, and direction is towards the V0 only, towards the velocity.